Okay, we're reviewing for the vectors test. In this case, I had been gone for the last several days because my son was getting married. It was amazing. I love the graduation, which best moment there is they throw their hats up and the jets are timed perfectly. Can't see them coming or anything because they're below the stadium. And then whoosh, you just go right overhead just as the hats kind of crest in the air. The jets go overhead. There's 6 of them and it's incredibly loud. And anyway, that was just awesome. And my son got married to an amazing young woman, and just very proud of him, and it was awesome. But anyway, I'm back now, and I want to try to cover everything that you possibly could need to know for the vectors test. So in the room, you are seeing a yellow ball. I know for the video you can't see it, but tell me in a position vector form where that thing is. Did you start with negative, and then how far did I say it was over? 2 or 3 feet? 2 feet. So -2. Okay. That means 2 to the left. And then the next number is how far to the right, up and down, which is 1. And then the last number is the z. It's the direction that's towards you. Raise your hand if you had -2, 1, 1. Okay, so you got your little position. That's where it starts. Now, here's a question, a typical question from the test. We want to make a vector that starts here and goes somewhere else. Okay? Do you get that that has an x, y, z in front? Does that ring a bell? And then it starts there. And then, see if you can finish this. I want it to move 1 in every direction. +1 in every direction. 1 foot, 1 foot, 1 foot. I want you to visualize that from this little yellow dot in the room, 1 foot, moving 1 foot in every direction. So I got a piece of wood here that's going to help me to do that. Okay, did you move to the right one? Did you move up 1? And then did you move towards you 1? If it's +1, it goes towards you 1. That's kind of what it would look like. Did you put 1, 1, 1 right here? And did you remember to put either a lambda or a t or some kind of a counter right there? Raise your hand if you had that part right. Awesome. Then there's one test question. You've already told me that you know how to do this. Next kind. I'm not saying that's for sure a test question, but that's a typical type of thing you'd have to do. Where is this vector at time 0? That's a simple question. Where is this vector at time 0? Because remember, vectors are an arrow, but even more like appropriately, they are a little guy running from one place to another. Because a vector has a place at a certain time. There's a time attached to these things. It's not just like a solid arrow. It's like a guy running on the arrow. And he starts at time 0 at the yellow ball. And then he goes in this direction, 1 to the right, 1 up, and 1 towards you. And where would he be at time 0? Well, if I put a 0 here, all that goes away, and he'd be right there. Raise your hand if you already knew that. Awesome. And if you thought at time 1 that he would be here, you're wrong. Figure out where he is at time 1. Where's our little vector guy that's running in this certain direction? Where is it? Think of it like a plane flying in space. Where is it at time 1? Now, we haven't done this before, but I think it's worthy. Remember in polar, we did, instead of an XY chart, we did an R theta chart. Could this kind of have a chart like that, kind of like an XY chart? Except it wouldn't be a TXY. Do you remember that? That was from parametrics. We did a TXY chart. This would be a lambda XYZ chart. You know what I'm doing here? At lambda 0, where is it? -2, 1, 1. At lambda is 1, that's time 1. Put a 1 right there. Then it would be -2 plus 1 times 1, which is 1, which makes -1. The x part, -1. Raise your hand if you had that right. Okay, then where does it go next? 1 plus 1 times 1, which is 1 plus 1, which is 2. And last but not least, we have another 2. Raise your hand if you had that one right. Awesome. So then, what if we wanted to see if that vector was parallel to a different vector? Okay, you remember where this guy is? He's up here. Can you imagine another vector that was like over here? That could be parallel to the first one? What would it need to be completely parallel? I'm going to get 2 sticks out now and show you completely parallel. If I had to have 2 vectors that are parallel to each other, I want to use the word slope. But there isn't really a slope for vectors. But what's the most like a slope that you see up here? You see this part right here is kind of like a slope. All right. I'd like you to take this original vector and write me the equation for a vector that would be parallel to it. And again, I've told you that this is kind of like a slope situation. You got to figure out which one's the slope, and then write me the equation for a vector that's parallel to my original vector, but just to clarify, is not the same exact thing as the original vector. If I change that starting point to a different starting point that, and now this is important, makes the dots a little farther apart or a little closer. Do you get why you wouldn't want it to actually have the exact same magnitude? Because if it had the exact same magnitude and the same direction, do you get they wouldn't just be parallel, they would be the same vector? Remember, if it's got the same direction and the same magnitude, it's the same vector. So you don't want to just make me another vector that happens to be the exact same length as the first one. Otherwise, its direction and magnitude would be the same. All right, so if you had started with the same point, I told you specifically not to, so that would just be really dumb, but why would this not be a different vector that is parallel to the first one? Because it's the same as the first one. And then if you also happen to stumble upon another spot where the magnitude of the vector would be the same, and it would be the same magnitude, and this is going in the same direction as this one, and therefore they'd be the same vector. So how do you make sure you have a different magnitude? Well, we better figure out if you know how to figure out the magnitude of these vectors then before we finish this problem. But the easiest thing is just to make sure it's not the same length. Maybe you go with 0, 0, 0 as your starting point. And it's going in the same direction, which would be a different. All right, so one thing at a time. Now let's talk about magnitude. I'm even confusing myself on that last problem. What if I start with 2, 4, 1? That can be a position, or it can be an actual vector. Do you get the difference? 2, 4, 1 can just be a dot in space, or it can actually be a vector that goes in that direction, 2 and 4 and 1. Would you please take a moment and say, if this is going to be a vector, I'm going to call it V, would you find its magnitude? Hint. It has to do with, if it had just had 2 dimensions, it would be making a triangle, like over and up, and then its magnitude would be like this. And use a squared plus b squared equals c squared. It's kind of like that. Find me the magnitude of this vector. Pause for a second while you figure out the magnitude of this vector. Okay, you should have said square root of 2 squared plus 4 squared plus 1 squared. Square root of 4 plus 16 plus 1. Square root of 21. Raise your hand if you had that one right. Awesome. That's how long this vector is. Because if it goes over 2 to the right up 4. See if I can model this one for you. I'll need a long stick. Where is my... If you go 2 to the right, up 4. Oh boy, that's going to end up above the ceiling. Okay, yeah, I can't model this one in the room. I'll do the next one. All right, now, if that's its length, what is the square root of 21? I have no idea, but I can tell you the square root of 25 would have been 5, so you get a little less than 5, like 4 point something. Okay, all right. Now tell me this. What would be a unit vector? That means a vector that's heading in the same exact direction as this, but has a length of exactly 1, a magnitude of exactly 1. Remember how to make these? This happened a long time ago. Before I left, I taught you this. The unit vector. I'm going to pause for a second. I'm going to put you in groups so you have somebody to help you in case you're stuck. Okay, unit vector. It's really, really simple. Here's the original vector, but it's too long. How long is it? It's like 4 point something. How do we shrink it down? We multiply it by 1 over its magnitude. 1 over root 21. Raise your hand if you had that one right. Okay, if you forgot that, process that for a minute. I just multiplied by 1 over its magnitude. That'll shrink it down to have a magnitude of 1. Okay, now what does that do? That gives us a nice, clean little vector that is heading exactly in the right direction, and it has a length of exactly 1. So, answer this question. I'm going to start with a whole new problem. See if you can answer this for me. I have this vector that's like a lawn sculpture, and it goes exactly in this direction, has exactly this length. Here's my vector. I'm going to call it vector z. And I want it to be 1, 2, negative 3. I like how this, like it's a dolphin or something. It looks really cool, and it's headed in that direction. But I want it to be much bigger because I want to make a statue out of this in a much bigger house. And so I want it to be 90 feet long, but in the same exact direction. Hint, you're going to use the unit vector, which, by the way, in case this comes up on the test, z with the hat, that means unit vector. You're going to want to use a unit vector as you do this. Okay, I'm going to pause for a second, see if you two can together come up with a unit vector that'll help you to give me the final answer of, give me a vector that's 90 feet long in the same direction. I'll pause while you give that a shot. Okay. To get the unit vector, this little guy's the answer to unit vector, you have to go 1 over its magnitude. What was its magnitude again? It was square root of, this is, by the way, the bars around it mean magnitude of. The magnitude of z would be 1 squared plus 2 squared, which is 4 plus 1 is 5, and then 9 is 14. Square root of 14. Raise your hand if you had that one right. Awesome. Then it's 1 over square root of 14, and then you just have to times this by 90, which is going to jump up on top, because 90 is 90 over 1, right? So then it ends up being 90 over root 14 times 1, 2, negative 3. If they actually asked you to multiply it out, you could, right? You just multiply the top, multiply the middle, and multiply the bottom. It wouldn't be that hard. Okay, so that would be a vector in the same direction, but 90 feet long. All right, next topic. I'm going to give you 2 vectors. I want you to tell me what you can tell me about these 2 vectors. What could you tell me about those 2 vectors? Tell me everything that you could tell me. Not everything, but find a few things that you could find about how these 2 vectors relate to each other. Talk to your partner, see if you get the same things. Okay, at least did you notice that they are parallel to each other? Okay. Are they the exact same vector? How could you know for sure? Could you figure out the magnitude of each vector? If you could figure out the magnitude of each vector, wouldn't the magnitude be the same? I think some people, and I think I goofed this up earlier in the hour too, have this misconception that that's the starting point and then that's the second point. That's not what it is, remember. Okay. If you found the magnitude for one of these vectors, are you going to do these two numbers, and these two numbers to like find the magnitude of the vectors? I'd like you to find the magnitude of that top vector. Just think it through, figure out the magnitude of that top vector. Pause for a second while you do that. Okay, if you haven't figured this out by now, this is where it starts, and this is how long it moves in those directions. So isn't how long it moves in those directions, isn't that the thing that's going to tell you what the magnitude is? So wouldn't you just do square root of 64 plus 1 squared is 1 plus 36? Square root of 101, right? All right. If this guy's magnitude is a square root of 100, anybody verify that? Is that what you got for its magnitude? If you wanted to, you could do the slow way, I guess you'd say, and find where it is at time 0. Well, think about it. Where is it at time 0? It's there. And then you could figure out where it is at time 1, which would be put a 1 here, and then you'd multiply that all out, and then you'd say, how far did it move? And then you'd realize, oh, it moved this far, and this far, and this far. Okay, so anyway, the magnitude of the first one's 101. Square root of a 101, sorry. About 10. Then logically, what's the magnitude of the other one? The same. So if these two have the same magnitude and the same direction, then aren't they the same vector? Yeah, they are. So how could you make it go in the same direction, but yet have a different magnitude? Somebody tell me a different set of numbers than 816 that would still have the same direction, but would make this have a different magnitude. I heard somebody saying 16, 2, and 12. Wouldn't that go in the same exact direction, but twice as far? And therefore, wouldn't it make it have a different magnitude? Magnitude would be twice as big. Okay, now, do you remember how to find vectors? Oh, sorry, pausing for a second while I fix this. Do you remember how to find vectors that are perpendicular to each other instead of parallel? What do we need to have between these two guys? Wait, I don't want them to be the same. That would make them parallel or equal, as in the same vector. But what has to happen? What has to be true about this guy and this guy so that they would make perpendicular vectors? You want their dot product. Remember dot product? They want their dot product to be equal to 0. So I can change these three numbers to anything I want as long as it's not 0, 0, 0. Because, why? Because if you had a vector that actually moved 0 in every direction, do you get it has no length? It would be the 0 vector. It didn't move at all. It starts at a point and stays at that point. That's called the 0 vector. And you remember what? One more thing about the 0 vector. What is its direction? It has to have a director, and it isn't a vector, so it's every direction. 0 magnitude in every direction. That's the 0 vector. Okay, so you can't use 0, 0, 0 because that's not really a vector. It has no length. It's the 0 vector. It's cheating. I won't let you do that on the test. But can you make up three numbers so that the dot product with these guys' dot product, would end up being 0? There are a ton of answers. Let me show you why. Say I had a vector like this, and it's for those on the video, I just have a vector I'm kind of holding up a random direction. Do you get that this would make a 90-degree angle to it? But so would this, and so would this, and so would this. These are all making 90-degree angles, right? Aren't they all different directions and therefore different vectors? See what I'm saying? And they could even start up here, and this is still perpendicular. And it's still perpendicular. There's a ton of them that are perpendicular to this one. So that's why there's a ton of answers you could have right here for these three numbers. Would you work with your partner and try to find three numbers for that vector that would make it be perpendicular? I'm going to pause for a second while you do that. By now somebody's got one. Raise your hand if you've got one. Yes, what'd you get? And let's check him and see if he's right. 8 times -1 makes -8. 2 times the 1 makes +2, and that leaves us with -6. And the 6 times the 1 would make +6. Awesome. His makes a dot product of 0. So his vector is perpendicular. Okay, find another one. There's a million different options. There's literally a billion. There's literally infinite sets of numbers that can make the dot product equal 0. Kind of like a little puzzle. Okay, so who's got another one? Raise your hand if you got another one. What'd you get? 0, -6, and 1. Because 0 times the 8 makes it 0. 1 times the -6 makes -6. And 6 times 1 makes +6. Awesome. All right, now I'm going to force your hand a little bit. Let's say that this first one had to be a 1. Figure out what the other two could be. Again, there's still infinite answers, but there's probably an easy one and a hard one. If that top number has to be a 1, try to find some other combos that'll give us a perpendicular vector. All right, so what do we have so far? We have a total of 1 times 8 is 8. How can we cancel that out? By putting a -8 right here. -8 times 1 makes -8. And then a 0 for the last one to make that nothing. Anybody catch that one? All right. How many of you were able to make at least one that was perpendicular? All right, that's pretty much every group. Okay, good. Now you know how to make two vectors that are perpendicular to each other. All right. Next, pausing for a second. Okay, 2-second reminder. We've been doing these so long that if they wrote it like this, would you get that that's the same exact thing? Do you remember that that's the same exact thing? One's just in column vector form. Okay, just a reminder that that means the same exact thing. All right. Let's see. Yes, the magnitude between two vectors, or the angle between two vectors. There was a formula that you needed to remember. It involved the function. Which function did it involve? It involved dot product, yes, but it also involves something else. Cosine. See if you can remember that formula that tells you the angle between two vectors. Pause for a second. Let me do that one. All right. Somebody probably thinks they've got it. What do you think? And I'm going to put a big star for dot. Okay, over. Yep. Raise your hand if you had that one right. Awesome. So, if I want to find the angle, what would I need to know to be able to find this angle? Well, I'd have to tell you my two vectors, right? And what would this A dots be? It would be the dot product of the two vectors. And then this would be the magnitude times the magnitude. All right, so here's two vectors. Now, some of you are going to get annoyed with the fact that these vectors could be in completely different places. And yet I could find the angle between them. Why? Because I can move this vector over here as long as it's the same length or same magnitude and same direction, it's the same vector. So it's okay if they're apart from each other. You can still find the angle between them because you can just move one over and keep it the same magnitude and same direction. All right, so here's my two vectors. 1, -2, 1, and 2, 1, 3. I'm going to call this vector A, and I'm going to call this vector B. Would you please figure out the angle between those two vectors? You will need a calculator, and you will need inverse cosine at the end if you're doing it right. Pause while we give that a shot. Okay, so what was the task here? It was to try to find an angle between these two vectors. You needed a dot product. What did you get when you did the that times that, that times that, that times that, and added them all up? What did you get? What goes here? 3? Yes? All right, good. Then the dot product's on the bottom. What was the magnitude of A? That was the square root of 1 squared, 2 squared, and 1 squared. 4, 5, square root of 6. Did you get square root of 6 for that one? Awesome. This one, 2 squared, 1 squared, and 3 squared. That'd be 9, 4, and it'd be 14. Square root of 14. So this is just a big nasty number. 3 over the square root of 6 times the square root of 14, and it's just some nasty decimal. And then you do inverse cosine of that. And then be careful, because what if you're in radians versus degrees? Do you get how one would be totally different looking than the other? If you get 1 for an answer, that actually might mean 1 radian, which would be like 58 point something degrees. Okay, so just know which one you're in. I would accept an answer in degrees or radians, but you better tell me what it is, because if it just says 1.3, I can't tell if you know if that's degrees or radians. Okay, all right, so what did you get? And tell me if it was in radians or degrees. I will use Dice of Destiny to pick somebody. Row 2, person 1. That's you. And did anybody get the comparable answer but in radians? I'm thinking it would just be a little over 1 radian. Yes?
About
1.2 radian sounds very believable. Because I know 1 radian is like almost 60 degrees and this is 70, so yeah, it makes sense. Okay, raise your hand if you had an answer that matched one of those two. Awesome. Okay, that's how to find the angle between two. Let's not belabor that since everybody got it right, almost, maybe. Let's see what else. Pausing for a second. All right, now the toughest kind of all. By now, I hope you get that vectors aren't just solid lines. If these two cross right here, okay, do you get that they might cross there, but at a different time? You haven't got that straight yet. Just because they touch, they go through the same point, they might be like cars going through an intersection. Think about this. You've all driven either in a car or you've driven it yourself through the intersection of 7 and 101. Okay? That means you've pretty much all been in the exact same place. Think about that. You just haven't been there at the exact same time. Otherwise, you would have crashed with somebody. You get what I'm saying? So there's lots of times when people are in the same spot, but they're not there at the same time. And it's like there's a little guy running on this vector and the little guy running on that vector. If they happen to be hit each other, where they're in the same place at the same time, then there's a collision. Okay, well, that's the question that we had on the packet a few times, and you'll see one like this. Do the vectors cross, first of all? And oftentimes they will cross, but the question becomes, are they there at the same time? All right, so how do you do this kind? Well, first of all, I got to tell you the two vectors. You write these down, please. Pausing while we do that. Okay, so here's our two vectors, the red one and the green one. We call it R and G, because they're red and green. The question is, do they cross? And if so, at what time? All right, so here's how you start this. First of all, do you remember making little equations out of this? Do you remember doing little parametric? They're kind of like parametrics. All right, I'm going to get you started. Actually, you know what? I think it'd be better for you to try to remember this first. See if you can remember how to make your little equations. You're going to make 3 little equations, one for x, one for y, one for z, and then you're going to set them equal to each other because you want them to be the same. You want them to cross, and you're going to see if they do. Try to make a little equation for x, y, and z for the red one, and a little equation for x, y, and z for the green one. If you get stumped in a minute or two, I will show you how that works. Imagine the test was right this second. See if you could do it. Okay, if you're not on the right track yet, I got to help you so you don't just sit there and waste time. This top row, the x, would go with that, that, and that. And so the x would be 1 plus 2 lambda. The y would be 0 plus 1 lambda. If you want to say lambda 1, just because they're in that order, it's fine with me, but 1 lambda looks a little more normal. And last we have negative 1 plus 1 lambda. Now do the same thing for the green ones. And then set them equal to each other. Pause, we give that a try. Okay. Now if you've caught on to this pattern, it's 2 plus 3t and negative 1 plus 1t and negative 2 plus 1t. Then, if you want two things to cross, you set them equal to each other, and you see if you get an answer that makes sense. So I'm going to take this one and set it equal to that one. And this one and set it equal to that one. And this one and set it equal to that one. I'm having a hard time telling if you guys are completely lost or if you already knew that. Raise your hand if you had that down. You knew what was happening there. Awesome. Good. Now, what do? Well, you have a system of 3 equations and 3 variables. Actually, we only have 2 variables and 3 equations. Because we have lambda, 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 and t. So we have just 2 equations. Sorry, we only needed really 2 equations. But did we? See, some kids will solve this and never even touch the 3rd equation. And they won't know whether or not they did it right. Do you get what I'm saying here? Do you get, you could solve this without even having that last equation? And if you never check your answer in that last equation, then you might have an answer that works for the first 2 but doesn't work for the last one. That'd be kind of like the lines are really close to each other, but in one dimension, they don't actually cross. They look like they're going to cross, but this needed to be moved over to make it cross. Okay, so bottom line, make sure if you do use only 2 of these equations to solve it, that you check it in the 3rd one. All right, so here's the easy prey. Lambda is negative 1 plus t, or t minus 1 is the same thing as lambda. That was the easy one to solve for. You could have solved any of them, but that's an easy one because it's already done. If lambda is t plus negative 1, then I can put that right there. And now I have 1 plus 2 times, what was lambda again? It was negative 1 plus t. And that has to equal 2 plus 3t. Why is this equation good? Because it only has t's in it. Once you got it down to only t's, it's easily solved. So now I'm going to go 1 minus 2 plus 2t equals 2 plus 3t. Then I'm going to put these together, and that makes negative 1. And now I'm going to subtract 2t from both sides. And I get negative 1 is equal to 2 plus t, and then I'm going to subtract 2, and I get negative 3. T equals negative 3. Here's a big mistake people make. So, they cross when t equals negative 3 for sure. Nope. All we know right now is that if they were to cross, that negative 3 would be the time that the t, the green one, would be at, if they were to cross. We don't know that they cross yet. All right. What's next? Well, when you're solving any system of equations, you find the first one and then you find the second one by just substituting that back in. First of all, how many of you had negative 3 already before I did? Awesome. Then Now let's take that -3 and stick it back in. Where? I don't care. Pick any of them. I'm going to pick this one. And I'm going to put in t is -3. And that means lambda, or sorry, I'm going to recopy this equation down here now. -1 plus lambda is equal to -2 plus -3. And that means if I add 1 to both sides, lambda equals -4. Did anybody else get lambda as -4? Awesome. Now, remember how I said that we really ought to check this to make sure it actually works? Let's use the -3 and the -4 back in this equation. If t is -3, and put it back here, and lambda is -4, does it really work? I get 7 on the left, or -7 on the left side. And I get -7 on the right side. Sweet, it worked. What does that mean? That means they do cross. I now know for sure that they do cross. Do they cross at the same time? No, because look, it'll be there at time is -3. That's for the t equation. This equation right here, it gets there at -3. The other one gets there at time -4. Those are not the same times. They go through the same point. But if those counters are at different numbers, which they were, one's at -3, one's at -4, they went through the same spot, but not at the same time. So then the last part of the question. What spot did they go through? What is the spot where they cross? Hint, take the green one and put in the right time, and you'll know where the green one was. At time is -3. I'll pause where you try that. If you put a -3 right here, did you get 2 plus -9 makes -7? Right? Did I do that right? Okay. And then I'm going to go -1, and that times that makes -3. That makes -4. And what's the last element? Say it if you know it. -2 and -3 times 1, -5. That's where they cross. But they're not there at the same time, so they don't collide. All right. If you want more help, I'll be here in the morning. You could watch the review video from last year to get different problems that were just like that. So if you do both of those things, you'll probably do great on the test tomorrow. That's all I got for you for today.